Hi everyone. We are still discussing introductory topics in view of preparing for the Calculus 1 class. In this section, we will discuss solving inequalities. Now, throughout the course, you will have to identify the sign that a given function will take on different intervals. In this section, we're therefore going to focus on strategies that will allow you to solve these inequalities. As before, factoring will be an invaluable tool, including in situations where solving inequalities are involved. Without going into too much detail, here are the steps that can help you navigate through solving inequalities that involve complex polynomial or rational expressions. First and foremost, you will want to regroup all expressions on one side of the equation or inequality, leaving 0 on the right-hand side. Simplify and factor the expressions that you have regrouped. Find the zeros of each factor you have obtained. These would be the solution to the initial equation if, for instance, we had the left-hand side equal to 0. To find the solution to the inequality, test the sign of the expression in all intervals that surround the zeros you have found in the previous step, as well as many values that cause the expression to be undefined. For instance, if the left side is a rational expression with zeros at the denominator. Conclude based on the signs that you have obtained from your inequalities. Here's a first example that involves polynomials on both sides of the inequality. So 3x cubed minus 4x squared minus 75x plus 2 has to be greater or equal to the quadratic 2x squared plus 30x plus 2. And if you recall our steps, the first step was to regroup all of the terms on the left-hand side, leaving 0 on the right. Step number 2 was to factor the left-hand side expression. Now, as a first step, you could recognize that 3x is a common factor, so the first operation that was done was simple factoring. This left x squared minus 2x minus 35, which is a quadratic, and the sum product method can be used to identify numbers that multiply to give minus 35, but also add to give minus 2. We conclude that m can be minus 7 and n is 5, or vice versa. Now, because the coefficient of x squared in the quadratic is 1, these numbers can be used directly as the factored form of the quadratic. So x minus 7 being the m, x plus 5 being the n, gives us the factored form for the quadratic we had earlier. So 3x times x minus 7 times x plus 5 is a factored form of what we had in the previous step, and we wish to make this greater or equal to 0, or at least to identify values of x where this left side is greater or equal to 0. In step 3, we'll find the zeros of the factored expression on the left. So you'll notice that 3x, one of the factors involved, is 0 if x itself is 0. X minus 7 is 0 if x is 7. And x plus 5 is 0 if x is minus 5. Now, in a product, obviously, if any one of these factors is 0, the entirety of the expression is 0. So 0, 7, and minus 5 are numbers that will guide us in our tests for signs. Here's step 4, where we will do exactly that. So notice how I've created a number line. Above the number line are the values that we found through the zeros, minus 5, 0, and 7. Below the number line, I've rewritten the expression 3x, x minus 7, x plus 5. This is the reduced and factored form that we had obtained and for which the signs will be tested. So our zeros tell us that the expression on the left is 0 at these moments. Now what we want to do is identify the sign of 3x, x minus 7 times x plus 5 in the intervals that surround these zeros. Left of minus 5, we could use a test value such as minus 6. And if we substitute minus 6 into the polynomial, we'll find that 3 times minus 6 is negative, minus 6 minus 7 is negative, and minus 6 plus 5 is negative. Therefore, the product of these three terms, all three being negative, will create a negative outcome. Now we could repeat tests such as this one for the other intervals to find the signs that 3x times x minus 7 times x plus 5 produces. Now remember that our goal was to solve this original inequality, but through algebra we had replaced it by an equivalent inequality, which was that 3x, x minus 7, x plus 5 had to be greater or equal to 0. So on our number line, we're looking for all values of x that provide either a result of 0 or a positive outcome. And from the picture, you can figure out that such results are obtained when x is between minus 5 and 0 inclusively, or equal to 7 or greater than 7. So in conclusion, our inequality is solved over the intervals minus 5 to 0 inclusively and 7 to infinity. The process of solving inequalities is obviously going to be more complex when rational expressions are involved as well. In such cases, we must take into account the possibility that these expressions will be undefined at certain points. So as a guiding example, we're going to try to solve the inequality x over x minus 1 is strictly less than 2 over x squared minus 1. Okay, so we want to avoid doing cross multiplication here, and I don't want to get into too many details about why that is. So rather than cross multiplying, we will actually regroup all of our expressions on one side as we did earlier with the polynomial. So I'm leaving 0 on the right hand side by carrying the rational expression 2 over x squared minus 1 to the left. The best way to combine these rational expressions will be to find a common denominator for them. So x squared minus 1 is a difference of squares and factors into x minus 1, x plus 1. You'll notice that the two fractions involved already have an x minus 1 in common, and therefore we're going to create a common denominator by multiplying the first fraction above and below by x plus 1. And then we can regroup the fractions as a single fraction, maintaining the difference or the subtraction that took place on the numerator. Finally, we can simplify the numerator, which we've done by distributing and collecting like terms. And we'll even go one step further, which is to factor the numerator to find its potential zeros. So the sum product method was used here to factor x squared plus x minus 2. Okay, so the expression on the left is undefined when x is 1 and when x is minus 1. And that's important because if the expression is undefined, then obviously it cannot satisfy the inequality. The numerator is 0 when x is minus 2. Keep in mind, yes, x minus 1 does appear at the numerator as well, but it cannot be both a 0 and a point where the rational function is undefined. Okay, so there's a 0 divider when x is 1, and that is what comes in priority. Okay, some of you may be tempted to cancel the common x minus 1s and simplify the rational expression by x plus 2 x over x plus 1. But remember that we stated that x equals 1 creates a 0 division. So we'd have to make a note that x equals 1 is prohibited. All right, good. So we're ready to move on to our next step, which is to test the signs. So again, above the number line, I've stated all of the values of x that create either zeros or values where the rational function is undefined. So actually 2 points prevent the rational expression from being defined, and those are -1 and 1. As for when x is -2, we have a 0 at the numerator, which is perfectly acceptable and creates a 0 result. As we did before, we could test for signs. So notice how there are 4 intervals surrounding the 3 zeros and DNEs that we have identified. And testing for signs would reveal that we have a positive outcome left of -2, between -1 and 1, and to the right of 1. Okay, so remember what we were trying to solve for, though? Our rational function, we were looking to make it strictly less than 0, and based on our number line, such a result is obtained when we are located between -2 and -1, exclusively, because this time an equality to 0 is not acceptable, and of course when x is -1, the rational expression is undefined. All right. Therefore, the original rational expressions that we were comparing in this inequality will be satisfied for all x between -2 and -1,